All right, perfect. Let's get started. Right, so good afternoon, everyone. I am Vishwa Parekh. I am currently the Technical Director of University of Maryland Medical Intelligent Imaging Center. We go by UME. And I would like to thank Jordan for inviting us to, to talk about this really interesting topic on federated learning. And so today I'm going to talk about the idea of federated learning and how it can help us go from competition to collaboration. So before I get into the details, uh, yeah, yeah. So here are my disclosures. So I'm currently being supported by, so my work is being supported by DARPA Shell program, and I am a review editor for Frontiers in Oncology. And let's get started. So first, I'll talk about AI in radiology. We've all seen in the past few years, AI uh, is being talked as it's going to revolutionize the field of radiology. We have seen so many applications that have come up with AI being applied for classification that you can see in this case. You can use it for diagnostic classification. You can use it for segmentation, where you can essentially take a radiological imaging sequence and segment out every tissue that is present in these images. And you can go further and try to start reconstructing these radiological images and essentially create newer sequences or reduce your training time. However, and there are so many more applications that are being developed for AI in radiology. But the major problem here is that a lot of these applications kind of stay within the research arena, and very few of these actually start to get translated. And the major reason for that is because of the data sets that these different problems are being solved on. For example, let me give you some examples of the data sets that are publicly available right now. So if you go to TCIA and if you search for brain MRIs or brain tumor data sets, you'll find a large number of different data sets. And similarly, if you go to Kaggle and if you search for chest X-rays, you'll find like close to 230 different data sets. The problem is that each of these data sets are kind of toy data sets. They're specifically or carefully curated to answer a specific problem or specific question, and they're not generalizable enough. And because of that, anything that's built on these data sets does not necessarily get translated to clinical workflow. For example, if you look at the RSNA pneumonia detection challenge, the challenge is about, can you build an algorithm that automatically detects potential pneumonia? Now, the problem is that for these different, like for this particular data set, it's not always going to be the case that your chest X-ray only presents with a scenario whether you have pneumonia or no pneumonia. You'll have scenarios where there might be multiple different pathologies that are present in your images. And in that case, this particular challenge or the algorithms that perform really well in this challenge are not going to do well in a clinical scenario. So the problem is that most of our work has been related to toy data sets. And that has been the major issue with the lack of translation of AI technologies into clinic. So now the question is that we have all of these really cool data sets. Can we combine all of these different data sets so that we can leverage all the information together to build something that is actually really useful? Now, some of these data sets might be private and HIPAA regulations would not allow us to share these data sets. Then these different data sets would have different imaging environments. For example, the different data types that these data sets might contain. So for example, some of these data sets have MRI, some of these data sets have CT, MR, and pathology. Some of these data sets might have only pathology. Some of these data sets might have only CT scans. So it's really difficult to combine all of these heterogeneous data sets. And then all of these data sets are geared towards a particular different task. And so not all of them might have been curated for a particular task. And then it becomes really difficult to combine each of these data sets. And then finally, it increases your computational complexity. So if you bring all of these data sets in one place, you not only increase your space requirements, but you now need a high computational or high performance computer to evaluate or train a model across all of these multiple data sets. And so this is where I would like to introduce you guys to this concept of federated learning. Now, what is federated learning? So the idea with federated learning is, let's consider this scenario where we have different hospitals trying to build different algorithms for their own local data sets. For example, in this case, let's say each of them are trying to build a brain tumor segmentation model using their own personal data sets. Now, hospitals would not be able to share data sets with each other, but these hospitals can share the trained models or can share the models that they're using to work with these data sets. So the goal here is that how do we leverage all the information that is spread across all of these different hospitals to build this good global meta model. So the way we do this is we create a federated server. What a federated server does is it connects itself to all of these different hospitals. And instead of sharing data sets, these hospitals would share their local models that they are trying to train on their particular problem. Now, what federated server does is it takes all of these local models and combines them into a global model. Now, this global model essentially would aggregate all the important information in each of these local models. And once you have this global model, the federated server would push this global model or distribute this global model back to these hospitals. And so this is how federated learning works. And you can do this in an iterative manner where the global model would eventually learn all these different characteristics of the data sets that are being trained at each of these different hospitals. So this is an example of a centralized setup for federated learning. There could also be a decentralized setup where you don't have a central server. Every hospital shares its model with every other hospital, and everyone does this in an asynchronous fashion where they just look at the models that are coming towards them, aggregate them, and then send it out. And eventually, whether it's round robin or in an ad hoc fashion, every of these different models would learn features across all of these data sets. So these are the two different ways in which we can use federated learning. So the idea with federated learning is that even when you're not able to share data sets, you can share models in a way that you can share features about these data sets and learn more global models. So in terms of applications, federated learning has started to make a splash in the field of medical imaging. So for some of these examples of really cool applications of federated learning, so one is a brain tumor segmentation problem. So where we have, it's very similar to the setup that I was just using to explain the idea of federated learning, where different hospitals or different places will have different brain MRIs, and each of them would be learning their own segmentation model. And the federated server would take all of this and learn a global model. And what these guys saw was that global model performed as well as if all of the data would have aggregated in the same place. So in this case, you don't necessarily have to share all of this data, but you're able to learn a model that in a way uses all of this data. Then similar applications were used for breast density classification, as well as more recently for COVID-19 classification. Even with all of these applications, what you're seeing is all of these are very homogeneous applications in the sense that your data set is very homogeneous. It's very much similar across all of these different places, as well as your task is also the same. But if you going back to the data that we were talking about, the TCIA data, each of these are different kinds of data sets. They have different imaging sequences, as well as they are trying to solve a different kind of problem. So what we really want is we want our models to work on different imaging environments as well as different tasks. So I'll give you a flavor of why federated learning is very powerful. It's because you can actually use federated learning in these scenarios as well. So first, I'll go through a couple of examples of different imaging environments. In this case, the goal was to localize different kidneys, and you had different centers having different imaging environments. So one center only had access to CT scans, whereas the other center only had PET scans. So they had different modalities. But the federated learning model was able to learn kidney localizations across both of these data sets without ever having to get access to both of these data sets. In a similar scenario, we had cross-domain tumor segmentation problems where one group was working on brain tumor segmentation, one group was working on breast tumor segmentation, and federated learning was able to combine both of these tasks into a single task where the global model was able to segment both brain and breast tumors. And finally, we did an experiment with multiple tasks. So for example, if one group is trying to do a pneumonia versus no pneumonia classification, if a different group is trying to do pneumothorax versus no pneumothorax classification, we were able to pull both of these different experiments into a central server where the central server was able to tell you whether there's pneumonia or pneumothorax or nothing at all. So this is basically what I'm trying to paint a picture here, is that this is just the beginning. And currently, federated learning has a lot of potential application in harmonizing all of these data sets and problems to build really powerful models that could actually translate into clinical practice. But there is, we need to proceed with caution, because there is, like, federated learning is not as secure as we think it is. So I would just give an example of how people are trying to figure out whether it's actually secure, what is the privacy level of federated learning, because in this case, we are working with medical data and we don't want any sort of data leakage. So very recent experiments have shown that if we have a client data that's not being shared, but if a model that is trained on client data is being shared, then if your server is a malicious server, then that server could actually take that data and reconstruct what the client data probably looked like. And this could have very high potential security risks. So when we are proceeding with federated learning, before we get into deployment, we have to make sure that the models or the frameworks that we are building are actually secure enough so that there could not be any leakage of medical data. So in summary, I would say that translating high-performing AI and AI frameworks is very difficult to go from toy data sets to clinical setups. Federated learning is a potential solution, and it could provide a path for us to aggregate knowledge across these multiple homogeneous and heterogeneous data sets. But we need to proceed with caution and make sure that our models or our frameworks are secure enough. And this is our team at UME. Right after me, Paul is going to talk about his work. Thank you. Stay in touch.
That's fantastic. Thank you so much, Vishwa. So I did have a question that I was wondering if you'd be able to talk about. So with regard to using the data sets from multiple different institutions, is there any kind of quality control or any kind of screening for the data quality that's done before being able to join the federated learning cohort?
That's actually a very good question. So yes, in practice, whenever so for companies and for different places that are actually deploying federated learning frameworks, they do a quality control to make sure that the institutions joining the consortium or institutions providing any data sets have a particular, like, meet a particular quality requirement. And this also leads into a different kind of attack that I did not talk about, which is called model poisoning attacks, where actually a malicious client or a client that's trying to destroy your federated learning framework actually provides with really bad or poor data quality so that it messes with the entire framework's performance. So yeah, these different quality checks are kept in place. And there are many different algorithms that are used to make sure that the models and the images meet a particular quality requirement without having to actually look at that data.
Fantastic. Well, yeah, I'm not seeing any additional questions in the chat right now, but thank you so much, Dr. Vishwa Parekh, for this excellent lecture on federated learning.